Morning, everyone, and welcome to the FAÇADE webinar series, episode 11. My name is Laetitia Marot. I am a Marie Skłodowska-Curie Fellow at the In-Renew Center of Excellence, and today we will talk about the seismic strengthening of buildings with cross-laminated timber plates on the facade. I'm very pleased to welcome our speaker, Dr. Iztok Šušteršič, who is a research group leader of the Sustainable Building with Renewable Materials Group at the In-Renew, and assistant professor at the University of Primorska in Slovenia. Dr. Šušteršič has previously worked in academic research at the University of Ljubljana and in private companies specialized in the design and construction of wooden buildings with an emphasis of ensuring their seismic resistance. He has led over 200 buildings projects and worked on or coordinated 15 national and international research projects dealing with timber and hybrid timber structures, new adhesives, and seismic analysis. Dr. Šušteršič's research focuses on seismic issues, developing new optimized building products with greater benefit for users and a lower impact on the environment. He is also the coordinator of the cost action holistic design of taller timber buildings that started just last week. Today, the presentation is recorded, and as usual, you can send your questions in the chat. I will read them to Dr. Šušteršič at the end of his presentation. So now let's talk about seismic strengthening of buildings, and Iztok, you can start.
Thank you, Laetitia. Okay, well, good morning, or well, still good morning, everyone. I see quite a few familiar names. Some of you already have listened to this topic before, so it's not going to be extremely new for you, but still, you may still remind you of something new. Okay, so without any further delay, I shall share my screen, and hopefully it should work. Okay, so seismic strengthening of buildings with cross-laminated timber plates on the facade. So the topic of this was actually my PhD research topic, kind of fits this webinar series on the spot because it deals with using sustainable, renewable materials to improve buildings made of non-renewable materials like masonry, concrete, and so on. So I want to tell you a little bit more about that. So just a short overview of how this lecture is roughly structured. So we would go through this problem description, the objectives that we sort of set out to achieve before we started actual work. A little bit about CLT, so cross-laminated timber. Then a rough overview of the strengthening system design. And then we would go through experimental and numerical simulations we did for purely CLT walls that were loaded in plane because they are the main mean of taking the new seismic loads. And then the unstrengthened and strengthened unreinforced masonry walls. So URM stands for unreinforced masonry. And then the strengthened and unstrengthened reinforced concrete frames, both with and without masonry infill, sort of a typical architectural or structural system for buildings in the mostly, let's say, southern part of Europe around the Mediterranean, where there is also quite some seismic going on. And then we would summarize and conclude in the very end. So coming to the problem description, this is a seismic map of Slovenia. You can see that here in the center of it, where the capital is Ljubljana, is a very highly seismic active region. Also in the northeast and on the southeast, very close to our one and only nuclear power plant. So the Izola and Koper regions, where In-Renew and University of Primorska are minorly seismically active, but nevertheless they are on the brink of this the Mediterranean part, where you have the meeting of the Eurasian and African plates, and therefore on the left you can see this European Mediterranean seismic hazard map. The more bright red or purple the color is, the higher the seismic intensity is. So you can see that Greece and let's say the west of Turkey, also most of Italy, is really seismically active. So Slovenia lies sort of on the brink of that seismic activity, but nevertheless, we've still seen quite a few big ones in the past. So the records go all the way back to the 14th century. Of course, in the 14th century, these were the earthquakes were not recorded in the way we record them now with accelerographs. There are written notes on what damage was left on buildings from, let's say, the 14th century. And based on the description of that damage, it can be implicitly assessed what kind of magnitude of an earthquake would be able to cause such damage. So the strongest one so far in the region of Slovenia is assumed to have a magnitude of 7.2, which is actually really high. That was in the beginning of the 16th century, close to Idrija. And then we've seen quite a few that were over 5.5. 6.1 was the one that really shook Ljubljana badly, about 125 years ago now, and the one we're bracing ourselves for in the next years. This is also one of the reasons why we're really pushing forward so much this topic of seismic strengthening, because there's a bunch of buildings in Slovenia and of course elsewhere that are in bad need of seismic strengthening. So you see there were still quite a few other quakes that followed that caused some damage. So the last one really caused damage, and also some victims, was in 1998 in Posočje. You can still see damage from that one here on the right. And we also have to look at this issue of seismic strengthening, or let's say just seismic threat, from the perspective of the legislation. So we have today the building codes, they're called Eurocodes, that give designers instructions on how to design buildings so they can sustain the earthquake forces when they occur. Now, of course, the Eurocodes are have only been around since 2008. So we have to look a little bit back into history, what was then. So in 1895, there was this big Ljubljana quake. And after that, there were actually some basic provisions introduced in the Austro-Hungarian Empire that sort of implicitly prescribed some seismic safety. So it was the number of stories was limited or connected to the thickness of the walls that were necessary to sustain, to support these stories. The number of, or let's say the length meters of walls were also prescribed. So there were some very basic provisions. However, we do consider this first half of the 20th century to have, well, I would say decently or not really super dangerous buildings built around. Because then after the Second World War, so after 1945, we have this really, really catastrophic period until 1963, when the first, very provisional, but still first codes were introduced on seismic design, because it was the after war period. So there was all this renovation going on, reconstruction, and there were buildings that were built at that time could go up to 10 stories, and they were made from unreinforced masonry. They were basically copies of projects of such tall, or let's say relatively tall buildings from the non-seismic parts of Europe, because everybody had forgotten in 50 years what had happened in Ljubljana. So these are the most problematic ones we have now. So Ljubljana has quite a few of these 10-story unreinforced masonry buildings that would pretty much collapse as dominoes if a quake like happened 130 years ago in Ljubljana would happen again. So in 63 we got the basic provisions, and then in 1981 we got decent provisions with demands not as rigid as rigorous as now, but still we consider the period from 1981 to be of decent, let's say, quality and safety. Now, as far as the number of building units go, you can see that until 1945 there were about 182,000 apartments built. And then from 1945, 1970, there were close to 250,000 of those built, of course, all over Slovenia. That doesn't mean only Ljubljana, but quite a large portion of those are in Ljubljana. So you have this really problematic period from the perspective of seismic safety, and a huge number of buildings being built at that time. So right now, the estimates are about 1/3 of people in Slovenia live in areas where a severe earthquake is possible. And of course, the estimates differ because no two quakes are alike, and of course their intensity can vary quite a bit. But about 30 to 70% of inhabitants in the capital could be potentially left homeless in case of a major quake, if it happened again in let's say in this area. So we have quite a big issue on our hands in terms of safety, public safety, not just public health, but just general safety. And this is all coupled with another issue. It's the thermal insulation of buildings. So the thermal insulation, at least in Slovenia, or I think in the majority of Europe, just started to appear after 1973, and it became more common after 1979. These are the years of the first oil crisis in the 70s. You can see here the spikes of oil prices in those years, and it's actually the first time when people realize, you cannot just burn more oil to heat your building up a little bit more. So thermal insulation actually started coming in. But before that, you have all these completely uninsulated buildings that need lots and lots of energy to keep warm. So the idea was to try to combine both of these issues, because the thermal insulation retrofitting is being done in Slovenia and also elsewhere, and the European Union is supporting it very much. But the issue is, if you just thermally insulate the building and put a nice facade on it, you've really done nothing in terms of seismic safety. So this is, let's say, a case of a building where you would say, well, the right part looks nicer. I'm sure it's potentially also more safe than the left part. It's pretty much just the same old problematic building. One part could have thermal insulation on it, so you would have a smaller gas bill or smaller oil or electricity bill. But in case there would be a seismic event, both of the parts would be just as damaged. So they actually give sometimes fake impressions of the building quality, which is even worse. So we need to renovate, or we need to retrofit all aspects of the building. So there are a lot more, let's say, advanced ways on how to do this. You don't have to necessarily just stick styrofoam onto a building and put on some contact facade, and that's it. There are also, let's say, more original ways, not necessarily cheaper, but there are other ways. So this is a case from Germany. If you've perhaps ever heard of the TES facade system, it was quite a big research project let's say, in German countries. So to have a modular system of retrofitting all kinds of buildings. So basically you take a 3D scan of a building, and then you make a completely new outer shell, and this these figures made from light frame timber, and these basically form a new envelope. You can also install HVACs into this new envelope, so you don't have to have any internal new installations made in the building itself. So it's all made prefab, brought onto the building and installed on the building. Now the issue is that one only takes care of the thermal. What we tried to combine is thermal insulation with seismic strengthening. So if you replace the light frame, which is, it's decent for supporting smaller, lighter timber buildings in case of earthquakes. But if you want to actually strengthen something like a masonry or concrete building, you need to have a slightly more rigid, robust, and especially strong system. And CLT does potentially offer that because it's a lot stronger than, for example, light frame. So, of course, one of the things you have to take into account is building physiques. This is something we really did not explore in depth in the project. So one thing is that the original walls of buildings are never completely straight. So you always end up with different gaps. The buildings are not made in laboratories, so you can have a couple of centimeters across the height of the facade, and you actually have to somehow close that gap. So the easiest way is to use insulation, but of course you have to be careful of the dew point so you don't get condensation. But this can technically be handled, and this is something we assume the Germans have done already. So we really didn't look into this building physiques aspect. So we were only looking at the strengthening part for the seismic. So why CLT? Well, if I assume some of you have, or most of you have seen this material, have sort of seeing the potential it can offer. So these are in short, like jumbo plywood plates, but they're not made of veneers, they're made of individual boards, lamellas. They can get really big, so they can be up to 20 even meters long. They're usually cut down to 13.5 meters to fit on trailers of standard trucks, and they're up to 3 meters, exceptionally even wider. So you can use them, and you can then use CNCs to cut them in the right shape, so you can cut them according to the way a building is made. So you can make window openings, you can make door openings, so you can basically tailor the CLT plates according to the facade of the building. So overall, they have large formats. They enable precise production. They have high strength, high stiffness. They have low mass, which is really cool for earthquake because you're not adding more mass that would then get accelerated and cause more forces. So you have a really low mass but high strength system. They have dimension stability because they have layers running in cross directions. So they're not like glulam where the lamination is only unidirectional. And they have good insulation properties by themselves. So even if you would not put on additional insulation, you would actually get quite something out of the CLT plate itself. Of course, the idea is to also put on additional insulation. But maybe comparing to a concrete solution where the concrete is basically completely uninsulative, CLT is way better. And of course, they are CO2 negative. So 1 cubic meter is 1 ton of CO2, even 2 tons if you take into account the substitution effect. So really sustainable way on how you could potentially strengthen existing buildings. So about the strengthening system design, well, one thing is using CLT, the other is attaching it to an existing building. So we did saw the issue of buildings not being completely straight, having different coordinates of individual stories. You have to compensate for that somehow, but the other thing is also how do you actually attach CLT onto concrete, onto masonry. This is a rough sketch of what we actually also tested later on. So basically you see the masonry wall with assuming it has a concrete interstory floor plate. Then you see some steel elements, and then you also see a piece of CLT at the very end. So we were basically using these steel brackets on one side to attach them to, and we were attaching them to the CLT, and then a steel plate with some attachment sticking out to be attached to the building. And in between you have this intermediary joint. So maybe sort of an animation. So you attach the steel plate onto the building. You bolt it on we're using M16 bolts. But let's say, so these are some just very rough calculations of what we did. And then you attach the steel bracket onto the CLT using 2, in this case it was SIGA Idefix connectors. So the connection of the steel plate to the building can handle roughly about 120 kilonewton, and the connection of the steel bracket to the CLT about 109. Now, in between, you have this sort of control system. So you just have 2 bolts that are then connecting the whole thing together. So it's like a 3-step joint, basically. And this one only has half the load carrying capacity of the outer 2. So the idea is that this kind of acts as a fuse. So you're only controlling your whole response of the whole connection, because the connection is made from 3 parts. You have to connect to the building, to the CLT, and you have to then bring this somehow together. Is that you're not, always wondering which part is going to fail first. We've intentionally made one part weaker, so you only have to deal with one part of the connection. And this is the one that controls the overall response of the connection, therefore also the overall response of the seismic strengthening system. So, and this is then in the end put together. On the larger scale, so you take a building, put steel plates around it. The idea why you would have steel plates going all around is in case you don't have a concrete plate, if you just have masonry, and if you put discrete bolts into masonry, you can have really high stress concentrations around one bolt, and that's going to be pulled out. So you want to smear the load transfer, to all around the building to a longer distance. So you have a smeared load and you have smaller, or you don't have stress concentrations. And then you put on the seats. And Of course, assuming these would also come from the factory, prefab, with all the installation, windows, and so on, put on them from the beginning. So this was the idea in theory. So then we were testing components one by one. And the first component to be tested was CLT. So the overall research was consisting of smaller sub-research, let's say, projects that were made with different outer partners. So this was made in Germany, in Stuttgart, at their MPA, so material proofing something. And so we were testing CLT walls with openings, and these had sets of LVDTs and then strain gauges installed all across them. So what we did was we basically were testing these as beams. You can see they were supported at 2 points here at the bottom, and then the force was being applied in the middle. So what we were doing finite element models and comparing them to the response of the experimental testing. So in this chart here, the top bottom, you can see there's like 5 columns, and the first 2 columns, the blue ones, are finite element models. It says MKE. This is Slovenian for FEM. So we had 2 types of FEM models. One was a homogenized model, one was a directly or explicitly modeled layered model, and then we compared them to the response of different walls types we had. So we were quite close. We were pretty much in the range of the experimental response, and we were using just characteristic values given from standard. So we did not do any explicit testing on the lamellas. So all the elastic moduluses and so on were assumed from standard. We also then did the, let's say, the ultimate limit state testing on CLT, but I'm not showing this here. So the ultimate limit state was quite offset from the finite elements because we were again assuming standard strengths, but of course the standard strength or the characteristic strength is way below what you actually get as a mean strength on such a system. Okay, anyway, so the next step or the next element we were testing were the unreinforced masonry walls. So our bread and butter of the system. So we thought of these old buildings made from unreinforced masonry. So this is the standard setup if you want to see how unreinforced masonry wall behaves in shear, in racking. So how it actually would be loaded during an earthquake. So you can assume this would be a column between, for example, 2 window openings. So, you know, it's about 1/2, it's, well, the specimen is exactly 1.5 meters tall. It's 1 meter wide, and this one was 25 centimeters thick because it's made of 2 rows of masonry or bricks. And then you basically apply horizontal cyclic load on top of that element. And the element is also pre-stressed in the vertical direction because the walls always have some vertical load acting on them. So you see you see here in the figure, you have vertical load being applied on top of this wall segment, and then you have the horizontal load being cyclically applied. So you actually apply 3 cycles of each displacement step. First you go, let's say, very small increments. So you go to 0.25 millimeters. So you go 3 times 0.25, 0.25, 0.25, 3 times that. And then you increase the increment. So then you go to 0.5, 0.75, all the way until you go to, let's say, 10 millimeters in one direction, 10 millimeters in the other direction from this middle 0 point. And what you're actually measuring is the ratio between the displacement and the force you are measuring in your horizontal actuator, the horizontal hydraulic jack. And you get this so-called hysteretical response, which is exactly the ratio between displacement and force. And the area that these loops cover is actually the energy being dissipated within the system itself. So this implicitly gives you the amount of energy you need to get to this level. So as you can see at 10 millimeters of horizontal displacement, so this is the very top right figure, you see that the walls are already pretty much completely cracked. And if you would be looking at the hysteretic response, you see that the maximum load, the maximum horizontal strength has already fallen by about 25%, which according to standard demands means the wall is not carrying any more load. Okay, now we had a response of the CLT, we had a response of URM, unreinforced masonry walls. So then we put the two together and saw what is happening in this case. And the first means of attaching it was using epoxy glue to stick it on to the masonry. You can see the gray layer of epoxy being applied on CLT, part of it also on the wall. Of course, this is a very ideal scenario because, again, this was a laboratory-made wall. In reality, these walls go like this. So there's almost no chance of you doing this. Maybe if you would be using a sort of more of a cement-based filler, so basically to concrete this gap between CLT and masonry. But anyway, so let me just show you what happened. So you can see the final setup here on the bottom right. And then, oh yeah, sorry, you can't see that because I made a short version. The whole thing, how it failed was that the masonry failed in tension or effectively in shear. So basically, it was not the problem of CLT or the epoxy adhesive. It was actually the masonry just pretty much came off, which was kind of expected. But we did get quite an increase in strength. Of course, as soon as the masonry comes off, as soon as you get the crack between the CLT and the masonry, the system is back to square one. So you just have the response of the masonry, basically have again an unreinforced structure. So this is kind of out of the question. And all the next systems we were testing different setups, were assuming to have mechanical connections between CLT and the masonry wall. So like the initial idea was the one that I was showing you at the very beginning in these renders. So we were using these exact steel brackets, like I showed you before. You can see them here, and so we were then bolting them into masonry and seeing how the response of such a system would be. So we did try quite a few versions before we actually got to an effective one, because the problem is, I showed you 2 slides before, at 10 millimeters of horizontal displacement, the masonry is already gone. It's not carrying anything at all. So the building is officially, it's collapsed. The CLT and the connections at 10 millimeters of horizontal displacement just begin to take on the load because they're so flexible. CLT is flexible, and the connections themselves also have some gap, some play in them before they actually grab hold of the specimen. So what we did was all these modifications of the connections to have concave holes with negative, basically negatives on so it would be concave bolts that really reduced the slip in these connections. We changed the bracket still a bit and so on. So all the way until we got up to this, let's say, version we really wanted to. So we got about a 30% increase in strength and 166% in the ultimate displacement. So let's say 2.6 times the original displacement. So we got to about 20 or something millimeters of maximum displacement before the whole system failed. So you can still see this was at 20 millimeters. The wall was really cracked, but it was still sustaining the load. It was still sustaining the horizontal load, the vertical load. And at the final stage, you can see that these bolts that were holding together the steel bracket and the wall failed in shear. And you can also see here at the very bottom, so at the top right figure, that the concrete foundation started cracking, which means that the force was actually being introduced into the foundation over or through the strengthening system. So not anymore through masonry, but also the CLT strengthening system was introducing load into the foundation. So this is, implicit proof that we actually had quite a good transfer of force. So then you take these hysteretic curves, you take the backbone, and then you make the backbone a bilinear curve. And this is, you see all the different tests we made. So the dark full line is unstrengthened, and then you have different kinds of strengthening. So we had 4 different types. A was the glued one, then you have B, C, and D, or the mechanically attached one. So you can see this D in the end actually made a difference we were happy enough with to carry on to further testing, or to actually model this system on a larger building. And then we also did we also separately tested the connections. So we actually got explicit response from the connections, because when you do finite element models of strengthened buildings, you want to have the exact response of that connection. You want to know how much a connection can take and what kind of a response it has, again, in terms of hysteretic curves. So you can see you have this horizontal response, the vertical response of these connections, again, in 3 stages: bracket to CLT, steel plate to masonry, and then this intermediary joint. And you can see that these far right or far left connections are pretty stiff, because I showed you at the very beginning. So they can technically take twice the amount of load that this middle portion can. And the middle portion has this wider hysteresis. This is where actually all the seismic energy dissipation is going on. This is our control joint. So it was kind of working in the way we tried it to, of course, with some minor, differences, but overall the idea was sort of where we wanted it to be. Okay, so this experimental data we collected during the testing, we then tried to use on the finite element model of a 2-story unreinforced masonry house. So like a typical representative, let's say, of this era from 1945 to 1963. So we did assume it has a concrete plate, but the walls were completely unreinforced masonry, pretty standard size. And we only analyzed one single wall setup. So we just took this front wall, you can see here on the left. So we assumed the vertical load would be, of course, also put on top of that building, on top of that wall. And then we assumed this CLT plate being put on that wall, being attached in these spots, so at about 1 meter spacing. So there were 10 brackets on the bottom, 10 brackets on top in each floor. And the response of these brackets was taken as we've measured it from the experimental testing. So we just used the backbone of the response of the spring that was modeled in the finite element model from the experiment. So the analysis to actually get here was really long, because we did incremental dynamic analysis, which takes quite a bit. But if you just focus on these 2 very colorful figures, you can see the differences between the unstrengthened and strengthened building in different segments of the building. So you have these, let's say, wall segments between the walls, and then you also have the, let's say, the beam segments above the windows. And the green color basically means no damage, orange is moderate damage, red is near failure, and purple is pretty much a failed element. So you can see that at a rather high ground acceleration, but still possible, let's say, in Slovenia, you pretty much have a building more or less failing if it's not strengthened. And then if you would have a strengthening system, it would experience moderate to strong damage in the, let's say, in one of the piers, but overall the reduction of damage would be quite substantial. So the proof is in the pudding, but we didn't do any larger scale testing of such a system, let's say, on the shaking table. However, we did shaking table testing of reinforced concrete frames, both with and without infill. So they were designed according to the 1981 code, which is actually quite decent. So they actually had quite some reinforcement, but this was kind of a part of another research project. So we just sort of jumped in with our system as well. This original building was intended for a research project dealing with the vertical upgrading of such buildings. So you had different vertical upgrades made of CLT, light frame, steel, glass, and so on. But we used the same building to actually test our, let's say, principle of the seismic strength. So I'm going to show you the results for the frame with masonry infill. So you can see how the building looked like on the shaking table. So 2 stories, about 5 meters tall. And on the right, you can see the chart of the vibration periods. This is basically how a building vibrates at what frequency. So the lower the frequency, the higher the frequency, the lower the vibration period, the stiffer the building. It's like, like strings on the guitar. So the higher they vibrate, the stiffer they technically are. And the thing is, when the building gets damaged, that damage causes the building to become more flexible because elements have cracked, concrete has cracked, masonry has cracked, and it starts to vibrate more slowly. So the vibration periods increase. If at the beginning, it's very stiff, after damage, it just starts to wobble a bit more. So after we were increasing the seismic intensity of the shaking table, you can see the damage started to occur. So the damage in the end was about this bad. So the masonry infill was pretty much cracked all around the perimeter. So the connection between masonry and concrete was gone. The masonry was starting to shatter itself. So at this stage, we put on the seismic strengthening panels and then repeated the same shaking on the shaking table. You can see that the vibration period has actually returned back to its original value. So the building was stiff again because the load of the seismic, of this earthquake, was being transferred on this new strengthening system. So the frame, the concrete frame with the masonry infill, was not taking the load anymore. All was being transferred through COT. So you can also see that on the foundation. Again, this is the bottom anchoring bracket. You can see the concrete has cracked because all the force was actually being introduced through that or those kinds of brackets. So not the concrete directly anymore, but through the strengthening system. There was also one additional benefit: the torsional rotation of the building was reduced. So torsion means how a building is rotating around its vertical axis. So if you can imagine, like, a ballet dancer doing a pirouette, this is the same motion the building is also doing. So it's not just going in one direction straight, but it's also doing this. And because one side of the building was cracking a lot more than the other, just so happened that there was quite a big difference between how much both sides of the building rotated. And that rotation was then reduced by quite a bit. So from 60% to 25%, because again, the load was being transferred onto the COT elements. So we also did finite element models of these frames, both without and with infill, and you can see the differences here. So the colors are self-explanatory. So if there's no color, it means no damage. Green, so no cracks, even no cracks. So if concrete cracks a little, it's not a problem. So if you have green color, it means just no damage, very small cracking. If it's orange, it's moderate damage, and if it's red, it's close to failure. So you can see the differences between an unstrengthened, strengthened frame at a certain ground acceleration. You can see where the unstrengthened is already failed at the interstory beam. The strengthened one remains intact. If you have a masonry infill, when the masonry infill in the ground floor is already failed, the strengthened one only has moderate damage. So to sum things all up, because I think I've already gone over my given time. So the unreinforced masonry structures, the experimental results demonstrated there is an increase in strength and displacement capacity of the unreinforced masonry wall setups. The numerical results show that building damage during earthquakes is lower, especially for stronger seismic events. For reinforced structures with and without masonry infill, the experimental buildings post-earthquake damage did not progress after the installation of strengthening, and the vibration periods decreased. Torsional behavior of the building was also reduced, and models showed that damage in both reinforced concrete frame and masonry infill is lower at equal ground acceleration when the CLT plates are installed on the structure. Now, there are, of course, some limitations to the developed system. We only tested a relatively small number of samples. So there is no repeatability available because we had a certain budget, and then we rather tested a few different setups than just to repeat the same setup. So for both unreinforced masonry wall samples and mechanical connections. Okay, this brings me to my last slide. Thank you for your attention. And now I will gladly take any questions you have.
Thank you very much, Iztok, for this very interesting presentation and also very impressive test that you are carrying out for measuring the seismic resistance. So yeah, if you have questions, please type them in the chat. And I had just a few questions for you. What percentage of houses are equipped with the seismic resistant setup design in Slovenia actually now?
With the one I was showing you, absolutely zero. In general, a very, very small portion. So there are a few cases, mostly when you have, for example, state-owned major buildings, like the parliament was seismically strengthened. A few of the bigger, older buildings under cultural heritage protection in the capital were strengthened. But these are very, very few cases. So in some smaller housing, most seismic interventions or seismic strengthening interventions were very basic. So mostly for buildings that have wooden floors, that have wooden joists, you can actually have the floor tied around so the walls don't fall out over their plane, and then when the wall falls out, the floor just crashed down. So some basic provisions were made. But in general, this is not very common. So if you ask me, I would say that out of all endangered buildings, less than 5% were strengthened so far.
Mm-hmm. Okay. That's a pity. And I think it should be more like a standard to use this design, because it seems like it's more a recommendation currently.
The thing is, so what the code says, so what law says now is basically if you have any interventions in the building where you change the load-bearing system in any smaller way, so technically even if you make a new door opening in a wall, regardless of how small that door opening is, regardless how many walls you have to make sure that the whole building fulfills the code demands of today. So that is quite a big deal, because it's not really easy to do that. Mm-hmm. And that's why we have so many under the radar interventions in buildings, unfortunately. But on the other hand, the statistic I was showing at the very beginning is problematic, and if a quake happens, it's going to be huge damage. Maybe not so much people dying. It's really just the amount of money that's then necessary to retrofit or just to demolish and then rebuild. And because Slovenia is a small country, if you have a big quake happening in the center of it, so where you have the capital, where you have all the ministries, all different functions, hospitals, in terms of GDP, it can be devastating. So if a quake happens somewhere in Italy, it's a big country. It can it can sort of refund its sources to let's say to retrofit, or let's say to assess the damage and to rebuild the city. In a small country, it can be devastating just from the GDP point of view. So this is something we've been banging about for years, but this only gets the news once a quake happens. So last year it was Croatia getting shook quite a bit, and there was again interest raised also from the politicians, but I think it all died down in a couple, maybe 2 months after the earthquake. Nobody was talking about this again. So last year it was the Croats that got shaken. Hopefully not too soon it's going to be us, but we're going to be, our professors always said at the faculty, it was a silly statement, but he said, every day without an earthquake, we're one day closer to the next one. So, but we don't know when that next one is going to happen, but it's definitely going to happen. That's the main issue. So
true. We have a question from David de Valence. I have seen some recent tests using a timber frame with attached OSB panels for this seismic retrofit purpose. In your opinion, are these systems or CLT retrofits better?
I would say it's the issue is if you can get to a sufficient strength with OSB and timber frame, you wouldn't really be doing that worse. So it's really a question of, I guess, how many layers of OSB do you use? But then it's also the question of flexibility. So in general, a light frame system tends to be more flexible than CLT. So in case of what we were doing, the CLT strength was not even proving to be the problem. It was the flexibility. So because especially if you're working with unreinforced masonry, it cannot take much of displacement. So if you're trying to strengthen or to fix a very brittle system with a very flexible system, you have quite a few issues on your hands. Perhaps, or what we were looking at is that CLT would actually be a good alternative to strengthen concrete frames, because concrete frames are quite flexible. So before any damage occurs, they can bend quite a bit. So if they can bend, also the CLT has actually a chance, to grab hold of them. And perhaps even a light frame system with OSB would as well. So,
Thank you.
for strengthening, let's say, older timber housing, I think also an OSB system could be used. So there was some research done in the US for these old multi-story light frame buildings in San Francisco, which tend to have, openings only, walls only in one direction, have a very flexible direction in the other direction. So there were different systems being tested there.
Okay. One more question from Václav Sebera. Could strengthening be also reached using high stiffness, high strength fibers like carbon Kevlar ones? Do you know about any application like that?
Yeah, this is pretty much the common way how it's done now. So the fibers, usually it's carbon fiber or glass fiber, mostly carbon fiber these days. They're attached directly to masonry. So there's also issues, or can be issues with that, because you can have delamination issues again. So the carbon fiber is really stiff, it's really strong, but again, they can have a really high stress concentration on that fiber. It's just going to be pulled off of masonry. So you have to follow, let's say, certain patterns, certain procedures on how you actually fix that carbon onto the walls. The issue with this classical system is that you more or less have to take all the envelope off until you get the actual masonry. So you have to take the facade off, you have to take the inner, let's say, layers of paint and everything off, which means you more or less have to move all the people out. And it takes quite a bit for that system to be installed, to be dry, that you put on the facades again. So that's why also people mostly avoid it. One of the ideas of this outer CLT, it could be also, let's say, it could also be steel for that matter, but it is that you only put things on the outside of the building so people don't have to move out. But on the other hand, it also means you're kind of limited to what kind of buildings you can strengthen. So if they have a nice floor plan, an even floor plan, if they have access from all sides, this can be done. If you have inner walls, you have to strengthen. It can also be done, but this is not something we did explore. But yeah, using carbon fiber and glass fiber is the currently, let's say, official method of how we do strengthening, also for concrete.
Okay, thank you. We have one more question from Maxidit Minka. How would your CLT compensate for the eventual loss of strength and quality due to direct exposure to moisture, like rains and sunlight?
In general, so the test I was showing you were without any sort of additional facade. So this was just for the research purposes of the actual strength and stiffness of the strengthening system. But in the final version, this would also be covered with a facade. So the CLT would actually never be exposed. There are potential places where leakage of rainwater could happen. So at the bottom of the building, and also on top, where you have the roof connection. So these are always places where moisture can enter such a system, and then you have a problem, of course. But assuming you have the detailing made correctly, and then the contractor also made them correctly, you should technically not have any issues with water after the system will be sealed up.
Okay. Thank you very much for this interesting presentation. Thank you for replying to the questions. And thank you to all the participants who joined us today. And I hope you enjoyed the webinar, and I hope you will come back again to see one of the future webinars. And I wish you all a great day and take care.
Bye-bye.
Bye.